Okay, good day. This is dual enrollment pre-calculus. I am Mr. Cully. This is lesson number 40, conic sections, the hyperbola. Let's get right to it. It is, in fact, the hyperbola, not the hyperbola. The second thing I'd like to say is please make sure that you download the notes for this one or use the pause button generously to make sure that you get the diagrams down. I probably won't spend an adequate enough amount of time on it. So please take your time as you move through this one. We are going to write the equation of a hyperbola in standard form. We're going to find the asymptotes of a hyperbola. We are going to use the properties of hyperbolas to solve problems, and then we're going to classify conics from their general equations. So first off, what is a hyperbola? Again, defining it as a conic, if you take those two conics and you run a plane parallel to the center line, and it passes through a single nap of the cone, then the intersection between the plane and the cone is called a hyperbola. And then also the hyperbola is the set of all points in a plane whose difference, or the difference of whose distance from two fixed points in the plane is a positive constant. So basically what that says is if you find the center or if you define a center and a focus, and you take a line and you draw a line from the center to the hyperbola and then the hyperbola to the focus, if you get those distances and subtract them, they will always be a constant value, that subtraction. And so we come to the equation of those things, and you'll see that these two equations for the standard form of a hyperbola look very similar to the standard form of an ellipse. And in each case, we want to say that the ellipse has a positive as a sum of the two terms, and the hyperbola has a difference of the two terms. That's one of the big differences between hyperbolas and ellipses. The second thing is that in an ellipse, the value that is bigger on the bottom determines the direction of the ellipse, whether it is a vertical major axis ellipse or horizontal major axis ellipse. In the case of a hyperbola, it is not this value a or b. It doesn't really matter what's underneath it. It's the order in which the subtraction occurs. So if the x's come first in a hyperbola, it is a horizontal transverse axis, and if the y's come first in a hyperbola, then it is a vertical transverse axis. And I know that that can be difficult for students, so please make sure that you make that distinction. Some definitions: the transverse axis lies on an axis of symmetry of the hyperbola. Its length is measured between the two vertices, and its distance is 2a. And when I say 2a, I am talking about this a here from the equation. The center of the hyperbola is the midpoint of the transverse axis, and the conjugate axis lies perpendicular to the transverse axis along the center of the hyperbola and has a length of 2b. And again, this 2b is this b right here, that b value there. So let's look at a general diagram of the hyperbola. And again, here's a place where you definitely might want to pause. And so parts of a hyperbola are these. The center, HK, goes right here. All right, it is the center of the hyperbola, and the black curve is the hyperbola. The vertices are here at B and C. They are maximums and minimums. All right, in this case, it's a minimum. Excuse me, and in this case, it is a maximum of the hyperbola. D and E are the foci of the hyperbola, and the length of A to B. So AB is A units long. From A to D is C units long. And then from A to F is B units long. And when I say A and B, again, I am referring to this A and this B from the equation. And then in the hyperbola, b squared, and again, this b squared is c squared minus a squared, whereas in the ellipse, b squared is a squared minus c squared. And again, the reason that that is true is because in a In a ellipse, C is actually closer to the center than the vertice. So if it were the same way for both in a hyperbola, or excuse me, in an ellipse, when you did C minus A, you'd get a negative number, and we don't want to have that. Some other notes that we want to talk about: the asymptotes of hyperbolas, the horizontal transverse axis. If you have a horizontal transverse axis hyperbola, then y equals b divided by a here, and then it's k plus or minus b divided by a times the quantity x minus h. And again, these values all come from this original equation. There's my a, there's my b, there's my a, there's my h. That's how I figure these out. It's just a plug and chug. And these equations for the asymptotes end up being these dotted lines. And again, the asymptotes are what the graphs tend to look like at extreme values. So if you were to graph one of these hyperbolas on a graphing calculator and zoomed out, it wouldn't take very long before it started to just look like these two dotted blue lines. And again, for a vertical transverse axis, everything is the same except it's A over B. The last concept that we have notes for is how to classify a conic section from its general equation. We look at the general equation, and it's a circle. If the A value and the C value are the same, why they don't have a B value, I don't know, but it's the way it is in the book. It's a parabola if A and C are equal to 0, or A times C is equal to 0. And that's actually very easy to look at, because if you have an x squared but don't have a y squared, it's a parabola. It's simple. All right, or vice versa. If you have a y squared but not an x squared, it's a parabola. It's an ellipse if when you multiply a times c you get a positive, and it's a hyperbola when if you go a times c and get a negative. So, and that has to do again with the standard equation of a hyperbola has this subtraction in between, whereas in an ellipse you'll have a positive value. All right, so I'm going to refer back to a lot of these previous slides as we do the practice problems, the examples that I have. And I have 3 example problems. So first one says, find the equation of a hyperbola with vertices -2, 1, and 2, 1, and foci 3, or -3, 1, and 3, 1. So just real quick, off the top of my head, I'm going to quickly kind of draw a picture of this thing. And so I'm going to place some pictures, some points. And so I'm going to say that this, let's get the right tool. I'm going to say that this right here is 1. And so I'm going to go 1, 2, -3 there, 1, 2, +3 there on my x-axis and my y-axis, like that. And so my vertices are at -2, 1 and +2, 1, and my foci are here and here. So I've got a graph that's going to look kind of like this, and I mean, you know, it's not perfect. We're just trying to get a general idea of what we're doing here. So since it looks like the axis of symmetry, my transverse axis, is going to be horizontal, I go back up to my equations here and I look for a horizontal transverse axis. That means the x values are going to come first. So I start with that equation. I'm going to go x minus h quantity squared over a squared minus y minus k quantity squared over b squared equal to 1. All right, so if we go back to this thing, the distance from the center to one of the vertices is the value a. All right, so if I go back to here and I want to figure out what a is, it's this distance right here or this distance right there. In both cases, that distance is 2 units. So I can say that a is equal to 2. That makes a squared equal to 4. All right. The next thing that I know is that this distance right here, and in both cases, it's 3 units there. Now, if we go back to this diagram here, we know that the distance from the center to one of the vertices is this C distance right there. So I'm going to say that my c is equal to 3, and that makes c squared equal to 9. Now we don't have c in our expression here, but we do have a way to calculate that in a hyperbola. We can say that b in a hyperbola, or b squared is equal to c squared minus a squared. So if I come here, I can say that b squared equals c squared minus a squared, and in this case it is 9 minus 4, and so I get b squared equal to 5. And if we come over here, this point right there is going to be our center, and so our center is 0, 1. And so I can just plug and chug now and say that x, and okay, so oops, I don't even need that because it'll be x minus 0 will just be x squared over a squared we know to be 4 minus y minus k, and k is 1, so y minus 1 quantity squared over b squared, which we know to be 5, and that's going to be equal to 1. So I put a box around that, and we move on to our next our next problem. Just one moment here. Okay, example, use the given equation to find the standard form of the hyperbola, then use the result to find the center, the vertex, the foci, and the asymptotes of the hyperbola. This is probably the longest one that we're going to be doing. So this looks like we're going to have to complete the square. And so we're going to rewrite, we're going to collect, just like we did for the ellipses, we're going to rewrite this by collecting our x's and our y's. And then we will move the constant to the right. So I'm going to rewrite this as 3y squared, and then plus 6y. And then I'll leave some space, and it'll be minus 5x squared minus 60x. I'll leave some space to complete the square, and then I'm going to move the other over and make it 192. And so now before I can complete the square, I'm going to need to do some factoring here so that I have my a value for the squared terms to be 1. So I'm going to bring a 3 out in front, and I'll have 3y squared plus, let's see here, 6 divided by 3 is 2, gives me the 2y, and I'll put a parenthesis there. I'm going to subtract, bring out the negative so I don't have to deal with it. And it'll be, I can factor out a negative 5, and then I'll have x squared, and then 60 divided by negative 5 will be a positive 12x, and then we still have our 192 there. Okay, so now completing the square, half of the b squared is going to be 1, and so I got my y squared plus y plus 1 squared, and then minus 5 times x squared plus 12x, and then half of 12 is 6 squared, and our half of 12 is 6, and then we're going to square it, and then we get my 192. Okay, and so plus, let's see here, since I'm adding 3 times 1 squared, I got to add it on this side, 3 times 1 squared, and then negative, so I'm adding a negative 5 times 6 squared, so I have to add a negative 5 times 6 squared. And so on this side, I have two perfect squares. I've got y squared plus 1, and then minus 5 times x squared plus, oops, I screwed that up. It's a perfect square, so let's do this right. It is y plus 1 quantity squared minus 5 times x plus 6 quantity squared equal to All right, so I've got 192 plus 3 is, let's just, you know what, let's just grab the calculator and do that real quick. We can do that real quick right here. It'll be, let's see here, 192 plus 3 minus 5 times 6 squared equals 15. Okay, so I'll come back here, we'll bring this back up, and we'll make this 15. All right, and so I'm going to divide both sides by 15, and 3 and 15 reduce down to just 5. And then 5 over 15 reduces down to just 3. And then I get a 1 there. All right, so after that, I've got my standard form, and then we're going to use this, find the center, the vertex, the foci, and the asymptotes. Okay, so the center is just HK, so it'll be -6, -1. And since the y squared came first, if we go back up to here, when the y squares, we have a vertical transverse axis. And so just a real quick little diagram here. If I go, let's see, it'll be -6. So -6 and then -1 is my center. So I've got a ellipse that's going to go like this, and it's going to go like that. All right, so my vertices are A units away. So there's my A. And so since A squared is equal to 5, that means that I can conclude that A is equal to the square root of 5. So it's going to be above and below that by square root of 5 units. And so let's see here. It'll be, my vertices will be -6, 1, or comma, -1 plus or minus the square root of 5. There's going to be 2 there. And then we know that b squared is equal to 3, that value there. And again, I'm just looking at the equation. And then from this expression, b squared equals c squared minus a squared. So if I go, oops, I want to go back to this one. If I go c squared equals, oops, excuse me, I did that. I just told it. It's b squared equals c squared minus a squared. Then c squared equals a squared plus b squared. And so 5 plus 3 is 8. So c equals 2 square root of 2. So my vertices, my foci, will be -6. And again, because they're going to be here and here, they'll be above and below the -6, so the x values don't change. And it'll be -1 plus or minus 2 square root of 2 for both of those. Now, the asymptotes, we have a vertical transverse axis, so we have y equals k plus or minus a over b minus x minus h. So we'll come down here and we'll say y equals k plus or minus a over b x minus h, and just check to make sure a over b, that's right. And we've got all those values, so y equals, our k is still -1, our a is 5, oops, that should be plus or minus, k plus or minus, a is 5, b is 3, oops, and I wrote k, we know what k is -1, and then x, and then h is -6, so I get plus 6 there. And I suppose we could simplify that if we wanted to, but that's good enough for right now. All right. I think I got everything. Yep, that looks good. Classify the general conic sections as a circle, parabola, ellipse, or hyperbola. So we're going back to this list, to this side. And so when I look at this thing here, I've got an a value equal to 1. The value in front of the x squared is 1. The value in front of the y squared is not b, it is c. And c is equal to 1, so ac, or a is definitely the 1. A is definitely equal to 1. This is a circle. All right. I have an x squared, but I have no y squared. So AC equal to 0. This is a parabola. And again, when AC is equal to 0, it's a parabola. And then this time I have an A equal to 4, a C equal to 25, AC is equal to 100. That is positive or greater than 0. Thus, this one is an ellipse. So ended with an easy one. And finally, we are finished. So the Star Wars fun fact of the day: during the original ending of Episode 6, Return of the Jedi, Sebastian Shaw played the role of Anakin Skywalker. But when 2004, with the release of the special DVD special editions, George Lucas replaced Shaw with Hayden Christensen, the young gentleman that played Anakin Skywalker in um, the prequel trilogies. Well, that's all I got for you today, folks. Have a good one. See ya. Goodbye.